Afternoon, everyone. My name is Guha Manogharan. I'm an associate professor of mechanical engineering at Penn State, and I also co-director our 3D printing center called Sim3D. I'm on the other end of the spectrum from most of you. I'm here with a problem, not with a solution. And this is a problem that I think a lot of you might be interested in helping solve, which is on multi-material laser powder bed fusion. So this is my partner in crime is Ajit Panisar from Imperial College London, who couldn't make it here. So what we're going to talk about today is a new processing method and all our stumbling blocks in terms of design at different length scales and opportunities. So with that, so the process snapshot is on the left, a cool looking micro CT of TPMS gyroid with copper, bronze and steel on the right, and a snapshot of multi-material powder deposition on a single layer as an example. So before I go further, I want to acknowledge Ajit and his student Jair Wang and my own student Jacqueline Griffiths, who have been fantastic in taking on a new manufacturing technology and going through all the struggling pains, which is always fun. So just taking a step back to give you a quick summary of what Sim3D is. So we are an additive manufacturing center, originally started with DARPA funding at Penn State. We have applied research lab as well as College of Engineering and Earth and Mineral Science. We are about 25 to 30 staff and 45 faculty who are using the facility. And we do all kinds of work in additive manufacturing, all the way from design to processing and testing and so forth across the MRL and TRL spectrum. And if any of you are ever going to be in the Penn State region, you have a open invitation to reach out to me. I'd love to have you come and see our additive manufacturing center. And of interest of these days, we are particularly interested in working in refractory alloys, high temperature ceramics, high temperature polymers, and new designs and methods and so forth. So with that, here is another quick snapshot of our capabilities. I think everything we would need in terms of laser powder bed, electron. We used to have an electron beam powder bed as well. Now we also have cold spray, binder jetting, and the list goes on and on. So if quite a comprehensive setup for both the academic aspect of lower TRL research as well as having full-time applied research lab staff who take that to transition to higher TRL. So that's been a lot of fun, and we do have some that could be potentially classified. So I also wear a different hat, which is a PI of my own lab in addition to co-directing the center. So we do leverage a lot of the design, and we do predominantly experimental manufacturing work, but with an emphasis on biomedical applications for direct metal AM, DLP for a lot of the orthotics, and if time permits, I will get into 3D sand printing. If not, if any of you are interested in leveraging design for sand casting, you might wonder why, because now we can 3D print sand molds. So a lot of the gating and all of the design challenges that foundries have known for decades could be completely eliminated. So the one that you see at the back, the CT that you see, we've shown consistently that we reduce casting defects by over 90% as cast, and flexural strength improvement of somewhere between 15 to 20%, depending on whether it's cast iron or nickel aluminum bronze, just by reducing the turbulence of the casting. You don't have to have a straight sprue. So anyways, not to digress there. So that's like a quick snapshot, and I was talking to some of a few of you yesterday during the networking, and we were talking about how do we make sure what we teach in the course or teach in the in a university is relevant to what they will experience in industry. So we have a master's in additive manufacturing and design. I particularly want to highlight the hands-on lab portion, which is the fun part in my opinion. Because I'm an AM guy. So students take all the design, processing, and engineering course, and in my course, if typically we have a case study, where these are grad courses, you will only get a grade if you successfully finish the project, or you get a deferred grade to buy more time. And I added this slide because somebody asked about how do you make sure those who are learning DFAM in school is also able to understand its industrial applications. So here is one example. So we always choose a project. This is like a like a $40 or Amazon Air engine, but you have to redesign it for AM, incorporate additional functionality, and you get a grade only if you have the same RPM or better. So I think we do these kinds of stuff when it comes to DFAM and stuff. It's been quite entertaining and quite rewarding, I should say. Here is a quick snapshot of we are just doing some testing on hydrogen fuel-based turbine engine component that is DFAMmed. I cannot show the exact geometry, but I thought I'll show you a much cooler looking experimental results and so forth. So with that, I want to get into why we got into this whole multi-material laser powder. But we originally started with looking at biomaterials. So can we achieve the biomechanical performance as well as the surface topology of human bone? That's what got us started in this path. So we started looking into different bone sites, looking at different geometries. We started looking into which of the self-supporting geometries would be most efficient in being able to achieve all properties of structural importance, surface importance for bone growth, as well as patient conformity, right? So we started looking into that, and we started learning quite a bit very quickly. Depending on which anatomy sites, you can prefer one type of TPMS over the other, because you do get very distinct ductile versus brittle transition behavior just under static. And now we have published this also on fatigue, where you can see different sections have different types of sheets have linear behavior with normal yield versus abrupt brittle behavior and so forth. And again, I want to go back to the motivation for all of this, right? So what you see there is just a schematic of what a cortical bone and trabecular or cancellous bone would be. So can we get the best of both when we go from varying different TPMs, which others have also done since we did this. So we started looking into what is the effect of pore size of certain types of TPMS sheets and its porosity and its mechanical properties. So it was quite interesting to see also. I mean, I'm not presenting it here, but we also saw quite interesting results when we did wet lab test in all of this, and we wanted to go further into looking into actual fatigue behavior as well. And what we found was a distinct fracture mechanism. These are all Ti-6-4, by the way, were pretty similar to what we would observe in a natural occurring bone. This is a signature paper in this field from 18 years ago. But I think the idea of being able to manage your yield behavior and also your fracture behavior was quite interesting to see how we can emulate that kind of behavior also for biomedical implants, because stress shielding is the number one problem, as a lot of you would know. So with that, we started thinking of what are the alternatives, because to avoid stress shielding and so forth. And the next time you walk down the supplemental section of your local grocery store, you'll see a lot of zinc and magnesium bone supplements. They're really, really good for bone growth. So we started looking into zinc and magnesium, and we noticed that they're not strong enough, like stainless steel or Ti-6-4. So you cannot make them out of the whole implant, but they are really, really good for osteogeneration. So that got us into looking into what if we can do multi-material, as this is one of the application domains that drove us. And so we got into work with Aerosint out of Belgium, who originally developed this for powder dye filling applications, but then we were looking at this from laser powder bed standpoint, and I'll briefly explain in a few minutes how it works. Kind of like a different thought process of multi-material deposition in a single layer and not just across layer. And we have been able to achieve somewhere between 150 to 300 micron pixel resolution, and been able to use it for a wide range of application, including heat exchangers, where you can have a really hot side, really cold side, or corrosion resistant marine grade alloys with structural steel. So we looked at this as more as multi-material AM that enables local functionality, because what people have been doing for a while with material jetting with the polymers, and even with some with the applications, you can see several of them here, we were kind of looking at it from metal, and that's what got us in working with Duan in terms of exploring. I'm really tired of doing STL files for all of this, because we would like to be able to assign local processing conditions to doing multi-material laser powder bed. So there are a wide range of applications. You can think of air electrodes, biomedical implants, heat exchangers, and the list goes on and on. So, but that's all like down the line, because we have quickly learned there are a lot of problems that we need to solve in order to be printing with one material and qualifying it in LPBF. For those of you who have done it, is a pain. Trying to doing it for multiple materials is even worse. But I think that's what makes it fun, and that's where I think, again, Sim3D having the balance of fundamental research and applied research has been very helpful. So this is the system that we have in our Pro X320. The reason we did that was we have already used the system with a wide range of in situ monitoring capabilities for single material, so we didn't want to reinvent the wheel. We know that we'll be giving up a little bit on the build volume, but we still decided to go with that. And I think we are the first one, as far as we know, in the US to have this capabilities, third one worldwide, and probably the second one worldwide with 3 materials. And you might wonder why 3 materials, because the powder recycling is going to be challenging. So we chose a third material that could basically be a filler material that you can basically melt a wall around, that follows the contour of your part. So what you see there at the bottom right is basically the video of the system working. Basically, you have the hopper on top of the rollers, or drums as they call it, and you have mesh that are around the drums, and each drum is associated with one of the materials, and the mesh of the drum refers to your pixel resolution. So what you have in figure A at the top left is basically a cross section of the drum, and what you have in figure B is the slicing of, for example, in this case PSU, and the student who did this went to Florida for undergrad and clearly sneaked in the Florida colors, as you can, because there is still Penn State color of white and blue, so you can see the slice information for materials A, B, and C corresponding to the 3 drums. And on top of the drums, you have hoppers. You are using negative pressure. Like, think of it like a clock. At 12 o'clock, you're using negative pressure, where the circumference of each drum is equal to your Y, and the height of your drum is equal to your X of your bill plate. So you're using negative pressure to hold on to the powder with all of the mesh, and right when your particular pixel is at 6 o'clock, it's tangential to your bill plate, and you synchronize it based on your RPM of your drum and your travel speed to depositing specific powder in specific voxel. This is really, really exciting, and it still is really exciting to get into this, because I think there are a lot of opportunities here. We have taken this system and we are building our own jetting system on top of it for high temperature ceramics, where one of the materials could be dissolvable, or you could just burn it during curing. And we are also exploring this system for using nano composites, for where one of this material could be ceramic, that you can embed nano ceramics in your melt pool. So again, low TRL, low MRL admittedly, and I have no qualms about it, because we have to be honest with the technology and figure out where the challenges are. So if any of this is interesting to you, please do reach out to us, because we are quickly learning there are a lot of unresolved and there are a lot of interesting challenges. And I also want to admit there are other methods of others that have also come up with different methods of doing multiple materials in a laser powder bed. Some you can only do it across layers. Some which are based on like suctioning of powders and depositing the second powder can do it within the layer. So the applications is, again, I think it's quite interesting. But what I would like for this particular audience is to get in mind, and again, looking at the really nice breadth and depth of presentation for the last 2 days, is we need to solve problems at multiple length scales. So for example, if you're doing multi-material testing, and again, we are going back to functionally graded materials, DED and welding and all their test standards, which we know does not apply directly to laser powder bed. So we have to reinvent a lot of there. And I'm a mechanical manufacturing engineer by trade, and I did okay in metallurgy, but it's coming back and biting me, where I really need to go back and tackle a lot of the fundamentals of phase transformation issues, so that we avoid intermetallics. So far, I think leaning a lot on laser cladding and functionally graded materials in DED world has helped us. But what I think is, again, this is kind of an open invitation for the CDFAM community to look at different length scales. So whether where you do CalFed or ICME for multi-material, not only looking at material compatibility, but looking at what should be the volumetric energy density across the transition, like from the transition boundary into your bulk part, is going to have a major influence on your structure and property. For example, in functionally graded materials, you can gradually grade it. Here we do not have gradual gradation, unless we are trying to trick the system into having 5 different layers of different powders and then going with the melt pool. But it's a band-aid to the overall problem. The same thing goes for laser powder interactions, where we need to understand the melt pool mixing, and I have some examples to talk about it. And the one that I think would be the ripe for this group would be the how do we go back to optimization, and let alone the uncertainty quantification with defect formation and so forth. So again, right now we are focusing more on the multi-material bone scaffolds, some battery electrodes, and surface fluidic applications, because what we know of single material laser powder bed, we have to now calibrate it for emissivity of different materials and understand its melt pool behavior. And same thing with micro CT, when we are looking at grayscale and ounce fill unit for different materials, how do we go back to micro CT and non-destructive testing using ultrasound or other methods, and mechanical testing with multi-material, and so we are doing some intermittent micro CT. Again, kind of like a low TRL stuff, but I think I've been really inspired with a lot of the AI talks today, because again, I think we have to have more of a different approach to what we have done classically here, because based on the alloy and the build orientation, even the slightest of part we have with multi-material, when we reorient it in your build plate, you completely drastically change your thermal conditions. And that does not exist, as to the best of our knowledge, process simulation tools for multi-material laser powder bed. Because, for example, in this case, when we did copper, tin, and low carbon steel, we found a lot of nano cracks around 300 to 400 microns away from the transition boundaries. And I think this is all, again, we did not optimize the process parameters. What we postulate is a lot of the bronzes heat, sucking a lot of the heat from the steel. So we are getting a lot of the residual stress effect. And we are kind of now dabbling a little bit more into how do we come up with mechanical interfaces, because depending on the density of the melt pool, you could have buoyancies and melt pool mixing issues as well. And we are looking at some of the mechanical interfaces that we could try to have both mechanical and metallurgical bonding, which is quite interesting. And a lot of you might be quite familiar with this geometry, the MBB. So we started looking into, okay, let's take the classical problem and apply adapt it for topology optimization for multi-material. In this case, it was multi-objective, where we wanted to optimize it both for mechanical loading and for thermal dissipation. So that's the reason why we have copper, chromium, and 316 stainless steel that you don't typically see printed together. So we use the alternating active phase algorithm. All of you know this, and I won't go into the nuts and bolts. But what I do want to point out is at this stage, and after what we learned after this particular project is, and again, we should have taken advantage of the third material, which could have been a little bit more conducive metallurgically speaking for material A and material B. The reason we did not was we thought we should not make the optimization routine complex to begin with. So we started with just these two materials, where we used our solver to identify the optimal MBB for both steel and copper for multi-objective. And again, as expected, we did find improvements in thermal conductivity of the overall structure. We definitely satisfied what was required for the mechanical loading conditions, and we verified this with FEA. I won't go into all of the details, and we also did DAC with all of this. And I think it's a classical problem. It may or may not be very industry relevant, but again, we wanted to start at some point. And we validated the FEA results with DAC and so forth. But again, I think the main takeaway for all of you is, at every length scale, there is opportunity to go back to think about computational design of material assignments, along with concurrent design of material structure and the processing conditions, and also thinking of how to leverage computational tools when we are trying to validate the in situ monitoring and our micro CT information and so forth. So again, I won't go into a lot of this detail, but again, the FEA is good. So, but I think there is a lot more opportunities here. For example, right now we finished a clinical study in collaboration with UPenn and University of Delaware on textured zinc. Now we would like to explore the zinc with stainless steel. So I would like to leave this as the last slide, as more as food for thought. So everything we know for laser powder bed and what we have learned from functionally graded materials in DED. Now there is an opportunity to kind of reimagine it, and that's why I reached out to Duan and said, I'm not going to come here with saying this is wow, look at what I did. It's going to be like, hey, I think we need collaborations from the computational design community, and we are very collaborative. So that was the reason why I'm here. And please do grab me during the breaks. I would like to talk to you if you are interested in this. And thank you.